Welcome to another lesson. Let's jump right into implementing gradient descent. The first step is to specify the loss function that we intend to minimize. Given what I've shown you, you might think to specify it according to the following equation. However, PyTorch allows us an easy way to specify the loss function. We can access the built-in loss function from nn.mseLoss. Very easy. The mean squared loss, and store this in a value called criterion, or a variable I should say. Not too hard. All right, the next step is to specify the optimizer that we will use to update our parameters. The optimizer will use a gradient descent algorithm, notably stochastic gradient descent, an optimization algorithm that we can access from torch.optim.sgd, as in stochastic gradient descent. You may be wondering what stochastic gradient descent is. The gradient descent algorithm I showed you before is known as batch gradient descent, which computes the gradient using the entire dataset by updating the weights based on the sum of the accumulated errors. This can be very bad, since imagine you were dealing with 1,000,000 points. Running the same batch gradient descent process as earlier, where you'd have to evaluate the accumulated error for every single data point, for every iteration, that would prove very costly. Whereas with stochastic gradient descent, it minimizes the total loss one sample at a time, and typically reaches convergence much faster as it will more frequently update the weights of our model within the same sample size. Although the expression for SGD is different, the general concept remains the same, such that we're still updating the weights towards the negative of the gradient. It's just that now with stochastic gradient descent, it's mostly computationally faster. Alright, back to our code. In the first argument, we specify the model parameters that should be optimized. In this case, model.parameters. And for the second argument, we must specify the learning rate, LR. A reasonable initial learning rate is 0.01. And recall that learning rate simply corresponds to the tiny steps that we would take to reduce the error in every iteration. These tiny steps need to be sufficiently small, since as the line is adjusting itself, you never want it to move drastically in one direction, as that can cause for unwanted divergent behavior. In the near future, we will look to implement adaptive learning rates and look to see how one can further fine-tune these hyperparameters, but for now, 0.01 should be enough to observe a significant, yet quick drop in the loss function. Alright, so now that we've specified the configurations for our training process, it is now time to train our model. We will train our model for a specified number of epochs. An epoch is simply whenever we perform a single pass through the entire dataset. As we iterate through this dataset, we calculate the error function and backpropagate the gradient of this error function to update the weights, as you saw earlier. Okay, so how many epochs should our line go through? Let's recall the concept of gradient descent, which updates the weights and biases of our network in the direction that decreases the error function the most. It's an iterative process, which is why we need to pass the full dataset through our model multiple times to ensure an optimized result. In other words, we need more than one epoch. If you simply specify one epoch, that leads to the underfitting of a curve, which doesn't capture the underlying trend of data. As the number of epochs increase, the more times it's able to update the weights of the neural network, minimizing the error, and thus producing optimal results. At the same time, you don't want to pass in too many epochs, since that can lead to overfitting, generally, which is a modeling error that occurs when a function is too closely fit to a limited set of data points. For this specific scenario, overfitting shouldn't pose too much of an issue. We'll see examples of it later on. We will just stick to 100 epochs, which would provide more than enough training iterations for our model. Alright, and now for every epoch iteration, for I in the range of epochs, given that for every epoch we want to minimize the error of our model such that the error is simply a comparison between the predictions made by the model and the actual values. Let us first grab the predictions with ypred is equal to model.forward x. So for each x value, we make a prediction using the forward method, all of which is stored inside of ypred, and then we compute the loss. We set loss is equal to the criterion, which we set equal to the mean squared error. And we will calculate the mean squared error for both the predicted values as well as the actual values y. Let's make sure I called it y. And indeed I did. And now for every epoch that we iterate through, we will print the epoch. We will print the epoch I. Let me make these into double quotes. Ran it by mistake. All right, so we print the epoch I that's currently being iterated through, as well as the loss associated with that epoch. Loss.item. Forgot my comma. All right, simple enough. And now in order to visualize the decrease in loss at every single epoch, what you want to do is before the for loop, we're going to set a list, losses is equal to an empty list, and for every loss that we compute, we will append it into our losses list. We do this with losses.append loss. All right. Now, having computed the loss, at every epoch we must minimize that loss. Recall in gradient descent, we must take the gradient of the loss function, the derivative. And recall to compute the derivative, we use the dot backward method. This was in the Intro to Tensors section. We call loss dot backward. And having computed the gradient, we update our model parameters with optimizer.step, using the optimizer that we initialized earlier. All optimizers implement the step method that's used to update the parameters of our model and can be called once the gradients are computed with the dot backward function, as was just done. All right, we're almost done implementing the training process of our model. Before the optimization step, we must set the gradients to 0, since gradients accumulate following the loss.backward call. And we do this with optimizer.0grad. Rest assured that every model that we train in this course will follow a very similar process, where we make predictions using our model, compare the predictions made by the model to the actual outputs, and based on that determine the loss, the mean squared error, and then we use an optimization algorithm, in our case stochastic gradient descent, to update the weights of our model in the direction of the least error, thereby minimizing the error function of our model as we attempt to minimize the loss iteratively to obtain a model with optimal parameters, the model that best fits our data. All right, perfect. And by running this cell, we can now train our model. All right, and notice that as the epochs progress, the loss gets significantly smaller, eventually converging at a minimum value of what seems to be 7.46. Although it's not 0, for our purposes, this is really good. You have officially trained a model using gradient descent to fit a set of data points. To better visualize the process, let us now plot the loss on a graph. On a new cell, we run plt.plot. The x-axis will be the number of epochs, range epochs, and the y-axis the losses. Also, before I forget, just a fair warning, if you get really weird results for this training process, just simply make sure to restart the runtime or reset runtime, whichever one, then rerun your training process. It should work after that. Anyway, back to what we were doing. Simply plotting the losses on matplotlib. And we will give the y-axis a label, plt.ylabel. I will name the y-axis loss, plt.x label. We will name the x-axis epoch. All right, now running this cell. This further clarifies that 100 epochs was indeed an appropriate amount of iterations to allow the model to eventually converge to a minimum loss value, as it seems to be dampening out right over here at around 7.4, allowing our model to effectively train to fit our training data. To visualize how well the model fits our data sets, we can now plot our new linear model by simply calling plot fit train model. Plotting this data. All right, so we see our training data and we see our linear model, which has been trained to fit our training data. And it seems like it fits it pretty well. Congratulations, you've just successfully trained a linear model to fit training data using gradient descent. If this is your first time applying a machine learning algorithm, then feel free to pat yourself on the back, as this accomplishment is a pretty big feat. In the next section, we will step it up a notch and try to build a classification algorithm. I'll see you in there.